Hello everyone, and welcome to my poster presentation. In this video, I will be talking about the numerical study of a Halbach array composed of permanent magnets used as an electromagnetic brake for a continuous casting mold. According to the World Steel Association, around 96% of the steel produced worldwide is made through the continuous casting process, reason why we study said process. In continuous casting, many quality problems of the process can be directly attributed to poor control of fluid flow conditions. The flow of molten steel into the mold can be controlled by electromagnetic forces, be it by electromagnetic braking or electromagnetic steering. An electromagnetic brake uses a static magnetic field to control the flow of steel inside the mold, enabling uniform casting speed and temperature across the entire mold width. There are different types of electromagnetic brakes: the local type, the roller type, and the double roller type. To reduce the steel defects originated in the mold during the continuous casting process, an electromagnetic brake composed of linear Halbach arrays is proposed. A linear Halbach array is a special arrangement of permanent magnets in which each individual magnet rotates inside the array according to its polarization, rotating 90 degrees from one another. This array generates an almost unilateral magnetic field, maximizing the magnetic flux density in one of the sides of the array, while it reduces it to almost zero on the opposite side. The proposed electromagnetic brake is composed of linear Halbach arrays focused around the narrow walls of the mold, two on each side of the mold in an upper and lower distribution. The methodology used can be divided into two. First, the magnetostatic model. In table number 1, we can see the proposed cases for the magnetostatic model. The validation case based on Han et al. Numerical work. It uses cuboid permanent magnets and a polarization angle inside the array of 90 degrees. The proposed case number 1 uses the same magnet geometry while changing the polarization angle from 90 degrees to 45 degrees. In case number 2 and 3, the cuboid magnets change for cylindrical magnets. For case number 2, the polarization remains of 90 degrees, and for case number 3, the polarization changes to 45 degrees. As for the second part of the methodology, it corresponds to the magnetohydrodynamic case model, or the MHD model for short. In this case, we have the validation case based on Han et al. Numerical model. It uses cuboid magnets, an angle of 90 degrees, and first, before going to the MHD model, we need to solve the fluid dynamics model. Then, once we have achieved a quasi-stable state, we import the magnetic field and solve the magnetohydrodynamic model. As for the mathematical model, a time-dependent study was carried due to the transient nature of the phenomena. We required the continuity equation, the momentum equation. As for the turbulence model, we selected the K-epsilon realizable model and the MHD model for the solution of the magnetostatic cases. As for the model geometry, let's start with the
geometries required for the magnetostatic cases. In this case, 3 geometries were required. The first of them corresponds to Han et al. Physical model, the second to Han et al. Numerical model, which both of them were used to validate our cases, and lastly the present model. In table number 3, we can see the dimensions of the mold section, the cuboid magnets corresponding to the physical case, the cuboid magnets corresponding to the numerical model, the cylindrical magnets, as well as the domain required for the magnetostatic model. In table number 4, we can see the dimensions of the mold for the MHD model. The mold, looking at figure number 1, item A, we can see the mold. It has a section of 0.23 times 1.45 meters. It has a mold length of 0.8 meters, a cooling zone length of 1.2 meters. In figure 1, item B, we can see the distribution of the electromagnetic rays inside the mold. As for the results obtained in figure number 2, item A, we can see a diagram of the physical model. We can observe 4 points in which experimental data was obtained. In item B, we can see a comparison of the magnetic field of the 3 geometries: the physical model, the numerical model, and the present model. We can see that the 3 of them are practically the same. So we can say that our model is pretty exact, generating the magnetic field originated from a Halbach array. In figure number 3, item A and item C, we can see the magnetic flux distribution corresponding to Han et al. Numerical model on the wide wall and the narrow wall. As for item B and D, corresponds to the developed model. We can see once again that the magnetic flux distribution is pretty exact, so our model is working properly. In figure number 4, we can see the magnetic flux density distribution for the proposed cases for the magnetostatic model. In item A, we can see the validation case corresponding to Han et al. Numerical model. In item B, we can see the case 1 for the developed model. In item C, we can see the case 2, and item D, we can see the case 3. In figure number 5, we can see in item A, we see a pretty asymmetrical flux, while in item B, we see that the asymmetrical flux has been corrected. Item A corresponds to the fluid flow before the application of the magnetic brake, while item B is after the application of the magnetic brake. As for the conclusions, cases with cuboid magnets generate a magnetic field of greater magnitude than their cylindrical counterparts due to their bigger volume. Cases with a 45 orientation inside the array generate a field with a more homogeneous distribution along the narrow face of the mold, at the expense of a slight decrease in magnitude in comparison to the 90-degree counterpart. The magnetic field generated by each of the cases is capable of correcting the flow of the liquid even in the cases of severe asymmetry. That will be all for my part. Thank you for watching.